There we go. So firstly, to say thank you and welcome to everybody who could join us today in person and virtually. Firstly, to everyone who's here in person, thank you for braving national rail strikes and it's horrible, horrible weather this morning to be with us. So we hope you enjoy today. And to our people online, thank you so much. We have people joining us from all over the world. We really appreciate your support and we hope that everyone finds today exciting and interesting. My name is Andy Skilton. I am one of the trustees of Stargardt Connected and I will be our chair for today. So I'm not going to speak for very long, but I'm just going to do a few housekeeping things before I hand over. So in terms of fire, we are not expecting a fire drill today. If the fire alarm should sound, it will be very obvious and we will need to go back out the way we came. There are green fire exits, but we will all guide and direct people. And we have staff from the building on site today who will help us in terms of navigating. If you have your phone on, that's absolutely fine. We know lots of you will use your phone for accessibility. If it is possible to mute the sound in case anyone gives you a call, that would be appreciated. Please feel free to leave the toilet. If you need to leave at any point, you are welcome to do so. Just go back out of the room and around the catering desk, but our colleagues at the registration desk will be able to direct you to the loo if you haven't found it yet today. And I think that's everything to get us started. So the first person I'm going to introduce today is Bhavna Taylor, who is our Chief Executive of Stargardt Connected, and I'm going to let Bhavna talk about herself and all of the fantastic achievements. She's also going to be joined by Ethan, her son, who is the inspiration for Stargardt Connected. Bhavna, thank you.
Hello everybody and welcome to our first Stargardt Connected conference. I can't believe we're finally here. It's really exciting. We were meant to have this around in 2020, in July 2020, but we had the pandemic, so we had to cancel it. So we're here today. So whether you are here in person or online, thank you so much for attending our first conference. Also, thank you to our generous sponsors who helped make this day possible. So we've got our headline sponsors, Associated Optical, got Belite Bio, Mira GTX, Revision Therapeutics, Claris Bio, and Moorfields BRC. And thank you to our wonderful speakers who are here today. We've got a full agenda and lots of different topics. I'm sure you'll find it really useful and learn so much. And there'll be lots of opportunities to also ask questions as well, whether you're online or here in person. And also our speakers have been very generous with their time. So if you're here in person, they'll be here around during the break time and lunchtime to speak as well. So I'm going to start a little bit about sort of how Stargardt Connected came about and sort of our backstory, my backstory. So I'm a mum and I have a son and he's got Stargardt's disease and he was diagnosed when he was just 7 years old. And I had gone to the opticians. I thought he needed glasses and the opticians had said that there was an issue with him seeing the sight clock. So he, with a prescription, he couldn't see the chart very well. They initially had said that he was making it up, and I knew my 7-year-old son, he wouldn't be lying about not being able to see. I then went a few weeks later to a second opticians and just for a sort of check up and ask the same question, and they actually said that he was struggling again with seeing the chart, and with a prescription it wasn't correcting his vision. So which I thought was really, I just couldn't, couldn't fathom out why he couldn't see. I always thought if you can't see, you wear glasses. So obviously alarm bells started ringing and I was wondering what to do. And I knew something wasn't quite right. I had heard of Moorfields Eye Hospital and I knew that there was a centre of expertise. So I actually did a referral myself to Moorfields because I thought actually they probably would know. So his diagnosis actually didn't take that long. It took a few weeks and saw Professor Michaelides, and he was then diagnosed with Stargardt's disease, which I had never heard of, and it just floored me. So you're told, that you've got this diagnosis, that your child is 7, and prior to that, we'd had no issues. So he had routine appointments every year at the opticians, and nothing had been picked up. So I never thought there'd be anything wrong with his eyesight. And then to be told that your son's going to lose his vision, that he's going to, that there's no cure and no treatment, there's nothing you can do about it. There was shock, but I was completely distraught. And I remember just being very tearful and really upset, and just worrying. Actually, you worry about because you know at that time you use your eyesight for doing everything. So my big concern was schooling. How is he going to learn? How is he going to be able to read the board and write and do things? And how is he going to continue his hobbies? Things like, he was in football and he liked swimming. And I was thinking also, he's such a sociable child and such a sociable person. I was thinking, how is he going to make friends if he doesn't, if he can't see them? So it was just, you worry about their future. You want your children to have the best life, and you want everything to be just right for them. And it was just a really, really, really scary time. So I just wanted to kind of reach out. So I remember having that conversation with Professor Michaelides, and I said to him, is there anything specific for Stargardt? Is there a specific Stargardt group? And he said, no, there isn't. He goes, but I've always been keen for something to be set up. And I said, I'm happy. No, I want to set something up, because for me, it was really important that I met other families. I met other people who had Stargardts, but also I wanted Ethan to meet other people with Stargardts. But also I knew that being with other people, knowing how they've lived their life, it reduces that sort of feeling of isolation. You have those shared experiences. Professor Michaelides said he was happy to help me. He then signposted me to Andy, who at that time was working for Moorfields BRC. So he was working in the patient public involved engagement team. So I kind of was quite persistent. There was emails that went back. I think there was quite a few emails, and I said to Andy, there needs to be something, and he was like, and I said, something has to be done. There needs to be something specific for Stargardt. You can't have this condition and not, you just don't know where to turn. And so there was a bit of pot of money, and I think subsequently Andy, Moorfields BRC created this Stargardt's Patient Day. Which was actually on March the 18th in 2017, and we haven't planned it, that it's 6 years on, but it's today. I was like, it just so happened, the timings that, so it's actually 6 years ago that we had this up. I was then asked to help shape the day and also speak on a patient panel, and I was like, yes, of course I'll do that. And so I was on the panel with, and there was Rhea, who was leading the, she's going to make me cry. And she's got tears in her eyes. I remember, and it was Rhea and it was Toby, who are our trustees, and there was also Rob, who can't make it today because he's up in Sheffield because of the rail strike, he can't come. And so yeah, a lot of the people from the actual panel are on our trustee board right now. So after the Stargardt's Day, it was a day like this where people were together, and I thought, you can't lose momentum. We've got people here, and there needs to be something, there needs to be an organisation. So I said, look, I want to set up a charity. And so we registered as a charity in 2019, Stargardt's Connected, and we've just I think we punched well above our weight. I think we're a small but mighty charity, and we've just grown. And so we've got our website, we've got our which we set up first of all. We've got our patient leaflet. We also did some research around vitamin A and Stargardt's disease. I think you'll have a leaflet, a booklet on your chair. Also downloadable on the website. We have set up a patient register. I'm not going to say too much about it because 4 in the afternoon is going to be talking about it. And we are global. We are, we are the only Stargardt's charity in the UK, but I think we're one of the only few Stargardt's formal organisations in the world, and we're just growing. So especially during the pandemic, when we had our Zooms and our sort of online meetings, we grew, and our team is growing. We've got fantastic people in our team. We've got Professor Michaelides, who is, can't find him, oh, he's there. So he's our medical advisor, and he's fantastic. We've got Franz Kremer, who I met in Iceland last year at Retina International Conference, and he's our medical advisor. We've got Hannah Dunbar, who's our low vision technology advisor. We've got Katrina Taylor, who's our Stargardt's, she's our ambassador. We've got Paul Appleyard, who's our Stargardt's advocate. A lot of them will be speaking today as well. So yeah, so we've just grown, and we're really ambitious about our charity. And we got the National Lottery grant at the end of last year, which will help support the community. Very recently, just last week, I found out that I've got a grant with Thomas Pocklington Trust. This is around education. So we're going to have a joint grant with another charity. So we're going to be doing a toolkit around education. So whether you are in primary school, secondary school, college or university, it's about what best practice is. So we'll be talking about that when we find out a bit more in the coming months or so. And very recently got an award from the Prime Minister. So we've got the Points of Light Award. You know, having this community, and I've actually got a personal letter from Rishi Sunak, and he says good luck today. So he says good luck to the so we've got his blessings as well. And so yeah, we want to grow. We want to. Our mission statement is raising awareness, giving support, and seeking a cure, and everything that rolls around that. And something we've talked about, a little seedling at the moment. I've spoken to Professor Michaelides and friends, and I think Rhea knows about this. Well, our team as well, about a research network, which would be sort of getting all the, working together with patients and professionals in sort of finding out what the landscape is in terms of Stargardt research, collaborating together and being able to sort of look at research priorities and drive research forward, because you need your patients for research. And we've got our group here, you're our community, whether you're here online or, we've got our Stargardt, you are our community. So you are the heart of, you're the beating heart of our charity. Every time we have our meetings, we always talk about what's the community, what our community want. Our communities, our patients, they're our doctors, they're our professionals, the other professionals, the clinicians, pharma. So we always sort of obviously want to work together and meet your needs, really. So there's ways of doing that today. So we've got a flip chart outside for your in-person, if you're an in-person attendee. There's 2 questions around how you found today, but also how you what you'd want from Stargardt Connected in the future. And also if we've got Ivan, who's a videographer, and Ray is going to be doing some patient and professional stories, so she might grab you at some point so you could talk about your experience, but also how what you want from us and how maybe the charity's helped you. But also if you're online, we've got chat option as well, and there's going to be also a feedback form that you'll be getting in a few days. And so I'm using time to hurry up. Okay, I think I'm forever, but yeah, thank you everybody. Enjoy the day. I'm going to go back to Ethan, because he's the reason that we set up the charity, and he's going to give a few words about his life and how he lives with Stargardt.
Okay. Hello everyone. I just want to talk to you about a quick experience of me having my condition. So I was diagnosed around 7, turning 8, and to be completely honest, I did not know what my condition was at all. I didn't even know I knew it was something to do with eyes, but I didn't know what it was. Then I was told I was going to go blind, not fully blind, but I was going to be visually impaired. And to be honest, I was upset for a little bit, but I've always had a positive mindset, and I think that's one of the key things to staying to being happy even though you have an eye condition. I think yeah, keeping positive mindset is really important within school and outside of school. I can get around many issues. For example, my handwriting, I use a laptop for 2 reasons. Number 1, my handwriting is atrocious. Number 2, I think it's just really, it keeps my workflow going, and it's just so much easier because I can organize all my files and everything like that. And that's one of the issues. That's an issue that I've tackled, and it's just really useful. Outside of school, for example, if I'm going to a restaurant, I'd use my phone to zoom in on a menu, or use a little magnifier or anything. I use my magnifier on my phone. But the charity has really helped me just, I think, find other people who have the same eye condition as me. I just think it's really useful to know how other people get around and tackle issues in their everyday life with the same condition as me. And it's just also really interesting to know. And also it's interesting to know that there's hope for a treatment or a cure that could happen in the future. But yeah, that's what I really want to say. But I think my main kind of message from this, in a way, is to keep a positive mindset and just try to live a fulfilled life, even though you have an eye condition. And to be honest, nothing can really stop you. And yeah, thank you.
Day, but I will be a strict fun keeper. So thank you, and notice we had some more people join us. So welcome to those who've arrived. Thank you so much for braving the weather today to join us in person. I noticed we have quite a few sort of young people in today, which is fantastic. We have a young person session running throughout today in the art room, where there'll be games, art, activity, which I think Ethan will be heading off to shortly. So if any of you would like to go and join that, yep, Ethan will take you up. So Ethan's heading to the back of the room now. So any of you who'd like to go and have a bit of fun instead of sitting here with us, you are more than welcome to. Right. So this now brings us on to the part of our agenda. We are running a little bit late, but don't worry, I have built a lot of flex into this agenda, so that should be fine. So we are delighted to start today by introducing Professor Frans Kremers from the Netherlands. Frans is a professor of ophthalmogenetics in the Department of Human Genetics in Radboud University in the Netherlands. He and his team have helped identify 32 different genes associated with inherited eye disease. And in recent years, Frans and his team have been really interested in ABCA4, the gene responsible for Stargardt disease, and he's going to talk to you a little bit more about Stargardt and genetics. Thank you, Frans.
Thank you very much for this nice introduction. Yeah, I want to first thank Dagmar Taylor for inviting me to this meeting. In October last year, I hurt my knee while playing table tennis. I think, well, what's that to do with an eye condition, right? Nothing really. But it kept me, like, you know, on the couch for several months, and I was not sure what I could do in the months to come. And I was not sure whether I could come to London in the first place because of this injury. I really could not walk, right? So the meniscus problem was there. Luckily, it got a little bit better over the time. And the physiotherapist worked wonders for me. And yeah, the last 2 days, my wife also accompanied me here to come to London. We spent the whole day in the Harry Potter Museum, and yesterday in the British Museum, and the knee is still working. So I'm really happy that that happened. So anyway, I'm here and happy to speak to you. So next 15 minutes, I will give you a small introduction into Stargardt disease and tell you a little bit about our 3 most recent and most interesting discoveries in the research that we are doing. So, well, next slide, maybe first. Yeah. Next slide, thank you. Hopefully it will come.
It's on the little screen, but
Yeah, it needs to be on the big screen too.
We'll get there.
So yeah, I will give a small introduction about typical Stargardt disease. Typical Stargardt disease has an onset between 10 and 40 years of age. It's quite broad as we look at this, and it is characterized, if you see it on the screen, with a picture. If you shine a light in the middle of the eye, you will see a fundus, an orangey fundus that has these yellowish flecks in the middle. And that's sort of typical for Stargardt disease, and how a doctor will see the first symptoms of the eye condition. And you will see it hopefully in a minute. And apart from that, also, you will notice that there will be sort of a degeneration or a death of cells that are in the middle, in the center of the vision. So that will be typical Stargardt disease. It was already mentioned that Stargardt disease in the classical form, people have mutations in the ABCA4 gene. So I just want to ask in this room, because I was talking to one of the Stargardt disease persons, whether they had know the mutations. So in this room, can everybody raise their hand that has ABCE4 mutations? ABCE4 mutations. Okay, that's about 10, 12, 15 maybe. So I guess there may still be people out there that have Stargardt disease, but do not yet know whether they have mutations in that gene, or they may have a mutation in another gene. That's also possible. But an eye doctor that has a good knowledge of the clinics of Stargardt disease will get it right in about 8 or 10 cases. But we also got DNA samples from all over the world. Just to give you that small message, we collected samples from about 3,000 cases from all over the world. And if we screen the complete ABCA4 gene for mutations, we can find these mutations in half of the cases. What it means is that not all apparent clinically diagnosed Stargardt cases have mutations in ABCA4. but most have. So if the eye doctor is really a specialist, he will get it right in 80% of the cases. But if that's not the case, then then it's less, and you could have mutations in other genes. So my advice would always be, if you don't know the mutations, have a checkup with your eye doctor and ask whether a genetic test can be done. And it's the first step in the process that will come afterwards. But it has different advantages to get this information. So I hope that the slides will be on the screen.
Yeah, sorry.
Could I work it from here? No?
Shall we try from there?
Yeah, please do. Because I can also work the slides. So share the file. Right?
No. There we go. I'm going to try and reshare. So apologies, everybody.
Oh, it's getting there. I think on my screen.
Check now. No. I'm going to go. I will go and find our technical support.
Okay. I will still can give you a little more information without the slides. So, so you could say that about 60%. Sorry.
Do you want the slides? Do you want me to? I don't have slides. Or are you going to keep on going? 'Cause it makes more sense to do genetics first.
I think it's still probably better, but let's see if you can solve it in 5 minutes, we're fine.
Sure.
So about I would say about 60% of all the, let's say, ABCC4 associated Stargardt cases, they have this classical form of Stargardt disease, and there's two other groups that also come into this picture. So already quite a long time ago, we also found that early onset Stargardt disease is also there, and we also found more recently that there's also late onset Stargardt disease. So at this moment, we recognize that, okay, we are almost there. It's getting there. Yes, almost there. Yes, okay. Thanks for technology. So I will talk to you about this typical type of Stargardt disease, and I will talk to you about what an eye doctor will see if he shines a light into your eye. And that's what you see here. So the onset is between 10 and 40 years. And classically, a person with this condition would have one severe mutation in ABCC4 and one mild ABCC4 mutation. So just keep that in mind, because it's important for my story to understand this. One severe mutation, one mild. And for the sake of simplicity, consider that all ABCC4 associated Stargardt disease persons will have at least one severe mutation in one copy they got from one of the parents, and they will have another mutation coming from the other parent, which can be severe, mild, or very mild. So next slide will give you the picture that I already talked to you about, the more severe end of the spectrum, where people would have two severe mutations. But you have a more severe retinal fundus picture, as is given here. Then the next slide will show that we more recently, maybe the last 8 to 10 years, appreciate that there's also very late onset Stargardt disease. And these people will have one severe mutation and one very mild mutation. And in fact, we even found some individuals that got a diagnosis of Stargardt disease at 75 years of age. So you can have a diagnosis between 8 years and almost 80 years, almost a full life expectancy. Next slide, please. And yeah, I already indicated that the classical form is seen in about 60% of the cases, severe end at 20%, and the more, let's say, the late onset also 20% of the whole patient group. Next slide, please. So talk a little bit about the protein. I will not go into much detail. Next slide. So if we look at the photoreceptors, the cells that capture the light that we see at this moment, the light capturing part of these cells, you can see them as a stack of pita breads. So think about 1,000 pita breads stacked on top of each other. And these pita breads at the rim, at the outside, they will carry the APC4 protein. And I'm not going into the detail what the protein is doing, but just that it is there in all these pita breads. Stacked, like 1,000 of them stacked in each of the rod cells. Next slide. And they are at the end of the rim of these pita breads because there's only place where there's space for this protein, because the protein itself has a certain structure that requires that it can only be sitting at that position and no other place in these cells. Next slide. So if you think about mutations, we can distinguish two major types of mutations. One type of mutation is that you have one of these building blocks of the protein to be replaced by another building block. We call those amino acids. So these are the building blocks of the proteins. And they can change from one to the other because of some mutation. And they can have a severe effect, a mild or a very mild effect. We just don't know this beforehand. Next slide, please. So this is this, next slide. There's this one. So you have one of these building blocks to be changed, and it has a small effect, it seems, at the protein level, but can have still a big effect, for the individual. And then there's another half of the variant, next slide, where the variant and the mutation itself will lead to the absence of the APC4 protein. So you have either a small change in the protein, and it can still be there, but it is dysfunctional, or you have a very severe mutation, and the protein is just absent. Next slide. So if you talk about genetics, I have to give you this picture also of DNA, RNA, protein, which are the different parts of the whole system that you have to know a little bit about. So our DNA, that is in chromosomes, is a double-stranded, like you could see it as a spiral staircase, basically, the DNA. And the APC4 gene carries 50 of these building blocks that each contains part of the information that makes a protein in the end. So we start with a double-stranded DNA, 2 copies of those for the APC4 gene, that is translated into, or is transcribed into RNA, which is basically a molecule that contains all the protein coding bits in a row. And then these are then translated into protein at the end, which is the APC4 protein. Next slide. Now, I'll tell you about 3 discoveries that we did over the last couple of years. And one of these 3 discoveries, this is the first one I will tell you about, is that although most of the mutations in APC4 are in these protein coding bits, these 50 different elements, where you find all these mutations, we found, and other people also found, that there's also mutations in between these protein coding blocks. So I call them here the in-between mutations. What do? Well, they give an effect at the RNA level. So they give an effect in the RNA, so the single-stranded, let's say, copy of the DNA, where a small piece of DNA is inserted into the RNA, which has no sense, which has no meaning. And it will disrupt this RNA molecule, and then also the protein will be not good, right? The protein will be off. And that's what we have with this kind of mutations. And we found about in 5% of all the mutations were of this type, the in-between mutations. And if you think about this, 5% of all the mutations means that about 1 in 10 individuals carry such an in-between mutation in one of the 2 gene copies, right? So, well, it's nice to know these mutations, but can we also do something about them? Next slide. Luckily, in principle, we can, because since these small parts of the sequence that come from the DNA into the RNA, which should not be there, we can also block out these elements in a certain manner. And for that, what we do is we synthesize a piece of synthetic RNA, small piece, just maybe 20 building blocks long. That RNA small molecule can be injected into the eyeball and thereby diffuse into the retinal cells, and in fact block the introduction of this erroneous block of let's say, sequence into the RNA. So next slide, or well, previous slide, sorry, just come back. So indeed here, what I show in the slide is that indeed a small piece of RNA can block this wrong part of the sequence where they will not enter into the RNA, and then a normal protein will be formed. And this type of therapy is called, well, an RNA modulation type of therapy. And it can be done for a certain subset of mutations, these ones that are in between mutations. And my colleague in Nijmegen, Rob Collin, is trying to use this technology to develop new therapies for this type of mutations. So it will serve only a small subgroup of individuals, right? Only like maximum of 10% of all the Stargardt cases, not all the other ones. Next slide. So I already indicated that we have a group of individuals that have this onset very late let's say in their life. They will get the first signs of Stargardt disease after 40 years of age. That we call late onset Stargardt disease. So they have a severe mutation on one copy of the gene and a very mild mutation in the other copy. Next slide, please. And so the second discovery that we did a couple of years ago, to my big surprise, because I think it has never been found for any of the classical Mendelian inherited eye diseases, is that we found for this group, which is 1/5 of all the individuals with Stargardt disease, that there were more females than males affected. So I told you a little bit about the classical form of Stargardt disease, where you have a normal inheritance, you have equal numbers of males and females to be affected. So now I am upsetting your knowledge about this a little bit, because in this late onset group, we find 2 times more females than males to be affected. And that's something that was not yet known at that time. And it's still debated also in literature, because not all the groups are finding this effect. We are finding it, and we are refinding it in large other groups. So, and we do not know what this means and why it comes about. We just don't know. But the fact of the matter is, if you have late onset Stargardt disease, there are more females affected than males. And it is really off what we normally know from Mendelian inherited diseases, because there you don't have this male-female difference. So this is different than what we know already. Next slide, please. So not only that we found this sex imbalance, that we have more females than males to be affected for this particular group, we also found in 3 families that we had siblings, where one sibling would have Stargardt disease, the other sibling would not have Stargardt disease, but they both would carry the same 2 mutations. Again, this is really strange and not very often found for recessive conditions. But clearly, and I show it here on the slide, one person is clearly affected with Stargardt disease, has all the signs for Stargardt disease, but in this case, the unaffected brother at the same age, or even 20 years after the onset of the disease in the other person, did not have any disease. And of course, we cannot completely rule out that that individual may still develop Stargardt disease very late in life, but at least 20 years after the onset in the brother, he did not yet have any signs of Stargardt disease. So again, there's something happening that we do not understand, why one person in the family has Stargardt disease and the other one does not. So again, upsetting your ideas about recessive conditions. Next slide. So I want to summarize this. We have late onset Stargardt disease, we just found more in females than in males. Then we have some persons carrying a severe and a very mild mutations, and where one brother is affected and the other one is not. Very strange. So next slide. It means there must be other factors, we call them modifiers, that play a role here, that must explain this. We just don't know what they are. Next slide, please. So for the last and third big discovery, I would say, because it was a big discovery for us, now that we know that we have this, what we think, genetic and maybe non-genetic factors that drive the disease in a certain expression modus, and sometimes even between affected and non-affected, we must recognize that there are many non-ABCC4 modifiers, factors that we do not understand, that have a big role in Stargardt disease. We don't understand them, but they are there. I don't even give you all the details of the clinical studies that have been going on, but it's clear that there are other factors that also contribute to this disease. So what it means is, could there also be some other things that we could find that we didn't find yet? So far, I just told you that the onset of disease is somewhere between 5 and 80 years that people are when they get the first signs of disease. So in the last couple of years, what we did is we designed a new sequencing method where we could sequence very cheaply all sort of genes that we know for the inherited eye diseases. And we collected about 4,000, 5,000 probes with these conditions, and we sequenced all of them for all the genes that we know of. And the patients were coming from all over the world, and we just completed the study, this massive study, and to our surprise, next slide, we found APC4 mutations, 2 severe ones, and 3 cases that have congenital blindness. So again, this is an upsetting new idea about Stargardt disease, because Stargardt disease classically is seen as a disease that comes in, at an age between 10 and maybe 40 years of age, maybe a little bit later, but most are in this range. But now we found 3 individuals, one from Australia, one from Canada, and another one from the US, where these individuals had onset of disease before the age of 1. So that's a very new finding, and we haven't published this yet. We are writing the paper as we speak. And it's interesting to think that how is it possible that we find this 25 years after the gene was discovered? And my only explanation can be that probably because it's so rare that it can only be found if you sequence many, many individuals. And in this case, individuals which were not suspected to have any Stargardt disease or APC4-related disease. Next slide. So I end up with this general concept that we now know that APC4 mutations can cause disease, written disease, from birth until 80 years of age. And the whole spectrum can be seen as APCE4 retinopathy. And of course, you could say this is Stargardt disease, but that's a clinical definition that's difficult then to maintain. Next slide. So the 3 discoveries that I want to just summarize is first, the APCE4 gene contains many in-between mutations, relatively speaking. Secondly, that people that carry a severe and a very mild mutation, they can show late onset Stargardt disease, and more often females than males are affected for this subgroup. And thirdly, that severe APC4 mutations, if you have 2 of those, you could also, in very rare cases, have congenital blindness. But that's quite new. Next slide. So I just want to end this talk by thanking my wonderful colleagues, and I just listed several of them already in some slides. But Celio Corradi, Dan Panneman, and Stephanie Cornelis are the main persons that did this kind of discoveries. And although I put a few names here from other collaborators, in fact, I have a collaborative slide with 40 more people on there, so it's too much. But I just want to thank all of these for the wonderful work. And next slide, I also would like to thank sponsors of the studies, among which the Written UK, which has been very generous to us over the several years of our research. Thank you very much, and I think we'll have questions after the 2 talks, right? Yes. Yes.
Does anybody have some questions now for Fran around this all? A lot to take in. Yeah, we definitely have a few. So Aitor's going to come around with the microphone and we'll ask Fran to answer some questions. Have you? Can we turn on channel 2? The mic up channel 2 for the microphone, please. Yeah. Perfect. Thank you.
I suppose if someone was interested in understanding which of those 3 categories that you went through, the classic, the early onset, late onset, you fell into, beyond, I guess, the sort of retinal imaging, the pictures that you put up to characterize each of those, and I guess your visual acuity, can the sort of genetic profiles that you've talked about also be quantified from testing your blood, I guess?
Yes, in the sense that the type of mutations will dictate a little bit whether we call them severe or mild or very mild. And this is more like the knowledge that we gathered over the years, looking at the different groups of individuals that have these mutations. But if you carry a severe and a mild mutation, you could still end up with an onset sort of at 11 years, but it could also be 40 years. And that is due to all these other factors that we do not understand. So there's a general picture that we can now draw, but based on the 2 mutations, we cannot really predict exactly what will happen in the let's say in the progress of disease. I think still the clinician will look at your eyesight and vision loss over the years, And after a couple of years, he probably can tell a little bit better what will happen over many years. But to know the mutation is probably the starting point, I would say.
And just, if I may, I don't want to have a million questions, but for those of us who are a little longer in the tooth and may have had that genetic test done 10 or more years ago, would it be necessary to sort of do another test now with the additional knowledge that's been gathered over that period, or would the original test have everything that was needed?
Well, a good question. I think if the two mutations that have been found were for sure, let's say, causal mutations, then I think it's not necessary to have a follow-up per se. But if you only have one mutation found, clear mutation, then I think it could be worthwhile to do a follow-up test. Because these in-between mutations, you only will find them if you also test in between these other elements.
Do you have a question from our online attendees?
We do, yes. Thank you. So there's several questions online, but this one is, why don't we use gene editing techniques like CRISPR to fix a mutation if we know them? And what is a risk and how far are we from a therapy like this? Which I'm sure everyone will be interested in.
I'm not entirely sure whether it also could be a small topic of Michael in his talk, but no.
Go for it. I mean,
Okay.
It's in its infancy, basically.
Okay, so gene editing is a technology that is quite new, and I think it's still not fully developed such that it can be used in clinical practice at this moment. So it's something that is sort of developing quite fast, but it only came about a few years ago. So it is still early days to say that this could be a good, let's say, therapy, because if you do gene editing or let's say variant editing, you always have to be careful that whatever you edit will not be ending up editing something else in the genome. So to do this very specifically at one location in the APC4 gene is not a small task. So that's why I think it's not yet fully there to do this in the clinical practice.
Sorry, can I ask another one, which is quite a few questions around the work that you've done to show the late onset and more women than men. Could it be due to things like being misdiagnosed with other conditions, or that women tend to live longer than men, etc.? Are there other factors? Are there, for example, environmental factors that might add into the genetic factors?
Yeah, so we don't know the answers to these questions, but we do know that it's not a bias that, for example, women would come in more to the clinic than men. So we corrected for all of that, and still there is a difference. So we just don't understand at the moment, and whether the hormonal system plays a role. that women go through different phases of hormonal changes, but that plays a role. But it's secondary, or we just don't know. To be honest, we just don't know.
We taking is another question? Yes. Thank you.
Sorry, you might have already mentioned this, or maybe I didn't understand very well. So if it's a mild and severe gene, does that pretty much just tell us when you're going to be diagnosed, or does it also tell you how quickly the gene will progress? And my second question to you is that, I'm from South Asia, I'm from Pakistan, my son has been diagnosed. And I wonder if the public register of genes is more limited there. And because when I got his results, there were so many genes, it was quite confusing. So can you tell by the report if it's a severe and mild gene? Yes. Are there some genes which are ethnic specific and which may not have been studied? And what does that mean for progression?
Okay, yeah, I think I answered a little bit already the question, but what it means is that if you have APC4 mutations in the report, then I or other people could probably tell you this is indeed severe or mild or very mild, and that will give a small answer to the question what the progression will be. It could not give the full picture, and still, because of all the other factors, we cannot say that these two mutations will give you this progression per se. And a healthy lifestyle is always important in any case. So that's always an advice that everybody will get from a doctor. But I think that's all we can say at the moment. And if there are another gene would be involved, then also you would need an advice of an expert that can tell you whether that gene with that mutation has a different progression for that individual later on. But that needs a specific answer to look at the result. I'm happy to do it, but I'm sure also Michael happy to do that. Yeah.
Another question. Yeah, one more question there before we move on. Thank you.
So it's really interesting to see. Thank you for your talk about the second point you made, which is the same mutation but very different phenotype. So, is there any understanding or hypothesis about why it is that the same gene doesn't necessarily cause the same disease for the two siblings, for example, that we talked about?
Yeah, so what we believe is that the remaining, let's say, functionality of the IPC protein, because if you have a severe mutation and a very mild mutation, there's always a little bit of remaining IPC4 activity, say between 30 and 35%. So if you are around that threshold, it could flip either way. That's our hypothesis. So other factors will either flip it up or down this threshold, and that will then determine whether you get disease, yes or no, or at what age you will get the disease. And we just don't know the other factors. That's the big issue at the moment. So we're trying to come up with studies how to find these other factors if they're genetic, but if they're non-genetic, then it gets even more complex. Of course, it will be very complex.
Thank you. And Red, anything else, Bernie, you just want to cover one more from the online audience?
I think most of them have been covered. I'll keep my voice loud. The only thing is it's more on the same topic. Could the mild mutations be associated to other genes related to retinal dystrophy or other conditions?
Yeah, but that already indicates that apart from the IPC4 mutations, there could be another gene involved that sort of interacts with this, right? And there are some preliminary data that this could be the case for proteins that are encoded by genes, for proteins that work in the same area, called these pita breads, at the rim. There are the proteins in the same area, so maybe there's an interaction there. But so far, I mean, the replication of some of the results has not been successful. So I think it's still out there what other factors could be if they are genetic. We just don't know them at the moment.
And I'm assuming that your work is going to continue, so some of these questions will be answered into the future.
Well, yeah, funding dependent, it will. And yeah, my team and also other younger people in my team, they will continue to do this for many years to come. So for sure.
Thank you very much.
Brilliant. Thank you very much, Fran. So our second speaker of the morning is Professor Michel Michaelides, who I worked with previously, know very well. Michel is a consultant ophthalmologist at Moorfields, for those who don't know him, and he works in medical retina, inherited eye disease, and pediatric ophthalmology, so he doesn't have much to do. And he's also a professor of ophthalmology at the UCL Institute of Ophthalmology, which is right next door. Michel's research portfolio includes 12 ongoing ethically approved studies, including one on Stargardt. And he's a principal investigator in 10 ongoing clinical trials, including some into gene therapy and stem cells. So he right at the cutting edge of some of the research that you would have heard about in terms of potential future therapies for inherited diseases. Michel's going to now talk a little bit about what the current research landscape in Stargardt looks like. And clearly, a lot of things still need to be addressed that are not yet in the pipeline. But thank you, Michel.
So Franz really has been at the cutting edge of understanding the genetics of ABCA4 with Stargardt disease. So we really should be congratulating him and his team. And hopefully he's not going to retire anytime soon. But at some point, I'm sure he'll hand it over. But in a nutshell, what he's been able to establish with the work he's been doing is that the genetics has some relationship to the point at which people start experiencing symptoms of Stargardt disease, be that in childhood, be that in adulthood, or be that in later adulthood. But yet it's not 100% relationship. So we expect to find more severe changes in the ABCA4 gene if you're younger than if you're later onset. But sometimes it doesn't kind of work like that, much as he's saying. And also in terms of within families who do harbour exactly the same changes in ABCA4, as he's described in an extreme example, you've got one brother who doesn't have any symptoms at all, and the other has typical Stargardt. that's very commonplace. So you expect the Stargardt disease that people experience to be very different both within families and between families. And as he said, what might account for that variability, which we actually see in all of the conditions that are genetic, it's not peculiar to Stargardt disease, it's all of the inherited retinal diseases. We think, could it be other genetic factors? Could it be environmental factors? And if those were teased out, and hopefully fans and people such as him will tease out other modifying genetic factors, those might also be targets for therapy in the future. In terms of the landscape for Stargardt disease, there's arguably, well, not arguably, there are more clinical trials in Stargardt disease than any other of our 300 inherited retinal diseases. Okay. And one of the reasons is that it's one of the more common conditions that we see. The other reason is that we have a pretty good, not perfect, but a pretty good understanding of the underlying genetics and how, when that gene is faulty, what changes it causes in cells in the retina, in photoreceptors and the pigmented cells, the RPE, and how that then subsequently results in those cells not working and dying and the kind of material that accumulates in the retina. And there are reasonably good animal models. There are reasonably good models for Stargardt disease that one can again tease out these underlying mechanisms, of what's the cause of disease, and also try different therapies. So those are the reasons why there's so much going on. And in terms of how many of us like to think of them, we bucket them based on the type of therapy that it is. So you have drug therapies, pharmacological therapies. A lot of those are taken by mouth or they're injected into the eye, into the jelly of the eye, intravitreally. And the majority of therapies are within that bucket, pharmacological drug therapies, in terms of number and in terms of how advanced they are. So they've got to phase 3, so the final stage of clinical trial before a company could try and get their drug approved. Okay. The other bucket of therapies that people probably know more about because it sounds sexier is gene therapy. Okay, and gene therapy is a wonderful thing. Potentially, our only approved therapy in the inherited retinal disease landscape currently, there'll be a lot more coming, but currently is a gene therapy. Okay, and that's a gene therapy for RPE65. So that is a childhood onset from birth, severe reduction in vision, both day and night vision. There are lots of other gene therapies going on for other conditions in the order of a dozen that are ongoing currently at different stages. There has been one for Stargardt disease. It started out as an Oxford Biomedica study, then became a Sanofi study. At the time that started, about 10 to 12 years ago, there was only one particular way the gene could be delivered into the retina, because the gene is huge, as Francis told us. It's a huge gene, 50 exons. It's a massive gene. And one uses viruses to deliver that gene into the retina. And it was so huge, it couldn't be crammed into the optimal viral delivery system. And so a different viral delivery system was used, which isn't as efficient as the one that's chosen. And that trial, whilst there haven't been any safety concerns, the efficacy, the effectiveness hasn't been overly overwhelming. And so there are different ways that people are now trying to deliver the gene, but using the optimal virus, which is AAV, it's called AAV. And there are lots of different clever ways people are trying to deliver it. They're getting ever closer to it being efficient enough because they can't cram the whole gene into there. So they're trying to break it up into maybe 2 bits or 3 bits. And then you have 2 different viruses having to be delivered, and those have to get together and infect the same cell, and then the gene has to be reformed. And so that adds other levels of complexity. But there are groups who are getting ever closer to that being an efficient enough process to then get into human clinical trial. Okay. And the other sort of large group of therapies would be stem cell therapies or cellular therapies. And if we take a step back and we think of the life of the condition, you have the early stage where you still have a significant amount of your retina that's present, and but parts of it aren't working very well, but they're still present. And that goes all the way through, it gets less and less, it loses function, it becomes dysfunctional, and then those cells start to die. And then you get to the other end of the spectrum where you have loss of most of the cells. So if you've got loss of the cells, you can't improve their function with gene therapy or drugs because they're not present to be improved. And so you need to replace the cells. And that's what stem cell therapy is about. It's about generating new photoreceptors, new light sensitive cells in the dish, maybe also the pigmented layer, that's the supportive layer for those light sensitive cells. And it may be that you need to deliver them both, or maybe just one, or maybe you need to put them in a sandwich. So there's still different ways of trying to work out what's the actual methodology to deliver those cells. And the light sensitive cells, the photoreceptor transplantation studies, are just about to start in certain conditions. So you'll have read of other stem cell therapies in retinal diseases, but they're not injecting cone photoreceptors, which is what is going to be required in Stargardt disease, plus or minus the pigment layer. So they're primarily injecting pigment cells in age-related macular degeneration, and we're learning a lot from those studies. And that's the Stargardt study that has happened with stem cells. So we were one of the sites involved in that study to see, can you put the pigment cells in, and might that stop the light-sensitive cells from dying? It was relatively safe. We didn't see much in the way of efficacy, and it may well be effectiveness. It may well be that you do actually need the cone cells, and the RP cells in isolation aren't sufficient. But I do anticipate those studies to start. And in fact, I wonder whether one of the first groups of patients that might be chosen for cone transplantation studies might be the late onset form that Franz is talking about, because it's quite a well-defined, delineated focal area of loss often, and it may be that you're almost looking to fill in the gap. Okay, you're kind of filling in the gap in the retina with your cone cells, and the surrounding cells maybe are not too ill, and that might be a better environment than having a whole landscape of unwell cells. Gene therapy is right at the beginning. It's where you've got a lot of cone cells still present, because you need quite a lot to be present to have an impact. So it's really early disease that gene therapy could work for. And there are different methodologies, genetic techniques, in addition to using a virus to deliver a normal copy of the missing gene or the dysfunctional gene, such as the CRISPR, where you're trying to correct the change in the actual DNA and in the genetic blueprint. So you hope to have a permanent fix, okay? But as Franz has said, there are many complexities about that, and one of those is, how do you make it only correct what you want it to correct and not correct anywhere else in the millions and millions of other letters in the genetic alphabet, okay? And again, there are great advances in that, and people are being able to be very specific and have developed technology to confirm that it genuinely is specific, that it's not going to change anything else and then have unpredictable and unwanted effects. The other way to modify genetically is, again, as Franz has mentioned, is at the level of the RNA. So not at the blueprint, but at the message that is made, that's then turned into the ABCA4 protein. And that would be likely to be a recurrent injection that would be done, but arguably potentially delivered in a less traumatic way. So there are pros and cons of all of these different therapies. And the repeated injection to correct those in between mutations that Franz mentioned, and that's probably the best target for this type of therapy, although other genetic changes might be amenable, have been tried out. So they are in the clinic. They are in patients in different genetic conditions. But the one that potentially could cover the entire spectrum to a certain degree, on the basis that this is generally always progressive and progressive throughout life, but the impact will be different at different stages of the condition, is drug therapy. So that could potentially be relevant across the entire spectrum of the condition, from childhood all the way through to, in older life. Okay. The drugs are being targeted at all the parts of the disease mechanism that we understand. So we think it's to do with, because as Franz has described, that this ABCA4 is in all these pitta breads, it has a role in recycling the light sensitive pigment, okay? And so vitamin A is part of that, and ABCA4 has a role in recycling vitamin A components. So there are drugs that are being developed to either reduce the delivery of vitamin A into the light cycle, the visual cycle, the recycled vitamin A. There are drugs to replace natural vitamin A so that it gets into the cycle and can't come out. There are drugs targeting the cycle, lots of different components to this cycle to try and slow the cycle. There are drugs trying to target the toxic product that seems to come out of the cycle when it is dysfunctional, when the ABCA4 isn't working right. You get an accumulation of toxic material that is always accumulating everybody, but in Stargardt it's doing it a lot quicker and a lot earlier. We're trying to tackle that. There are also drugs looking at what's the response to that toxic product. So there are inflammatory cells and different inflammatory mediators and chemicals that the body makes to sort of try and get rid of this noxious material. The drugs that have been in trial most, the ones that target the cycle itself. Okay, so they're the most advanced. Now the issue with the cycle itself is that how do you slow the cycle so you make less of this toxic material, and maybe the retina can get rid of that, or at least stop the negative effect of that toxic material, but not slow the cycle so much that you have a detrimental effect on vision, because you need this cycle because it's helping you see. But if you slow it so much, it makes your vision worse. And so if your vision impaired, you don't really want your vision to be worse, but you're told that, well, you'll have vision for longer, but it will be worse. So you kind of need to titrate the cycle, get it enough, slow it enough, but not too much, is not straightforward. It's proven not to be straightforward at the moment. So people do experience some side effects they don't really want. The effectiveness, there's been a signal that it does work if you slow the cycle, but there needs some more refinement in the actual clinical trials. So one of the clinical trials that reported that was targeting the cycle is actually Seller, Kubota, a Japanese company. Mixistat was a drug. It targeted RPE65, the name of the enzyme. And they've looked back at their data, and when they pass out a certain so patients with certain features of their Stargardt disease, they find that the drug did work. It slowed things down by about 20 to 30%. So they are optimistic that if they redesign the study, do the study again, they'll have a positive effect. So that's probably coming again soon. The other trial that hasn't published but has presented some data at some meetings is targeting vitamin A itself. So that's the Alkia study. That's I can never remember if it's deuterinated or protonated. They've changed the vitamin A in some way that it still participates in the visual cycle, but it doesn't come out. And so it's used preferentially rather than natural vitamin A you're taking a diet. That gets into the visual cycle. It doesn't get out, so it allows you to see. Shouldn't have a negative impact on vision because it has the same role as natural vitamin A, but it doesn't come out, so it can't form all this toxic metabolite. Again, some of the data they're showing is proposing a 20 to 30% slowing of the rate of change, which would be great. They're going to need to do another study because, again, the control group, the patients who weren't receiving drug, was rather small, and then they tried to use another control group and from a natural history study to make that comparison. So it's very promising, but I think it's very likely it's going to need another trial, another phase 3 trial to potentially get that approved. The final area I'll mention is the delivery of vitamin A into the cell. You need a protein called RBP4, what it's called. And there are 3 different companies that are targeting RBP4 to inhibit that, to stop vitamin A getting in the cycle. And some of those are very titratable. You can really sensitively change the dose of the drug you're giving and thereby change the dose of inhibition to kind of hopefully get it right, that you're getting enough inhibition that you're, again, slowing the cycle, but not so much that you have a negative impact on vision. And so one of those 3 is in clinical trial. That's the DRAGON study, cool name, I mentioned that before, DRAGON study. That's Belite Bio, and that's in the childhood onset Stargardt disease, so adolescents. So that is in trial currently, and it's a global study, phase 3. The recruitment target's been recently increased. We're actively recruiting in London. We're top of the charts there. We're not often top of the charts in recruitment, so that's why I'm sharing that, because I'm proud of that. So that's a study that I am, again, optimistic about, because I just like the concept of it not being the cycle itself, and that there's a degree of titratability about it. But, you know, it's only once the trials are done can we tell if they work or not. But I remain optimistic, and I'll draw a line there. Oh, okay. That's probably lucky for the people, though, wasn't it? They don't really want to see my face, do they?
Thank you, Michelle. One right over there. Start over there, and then where I'll come to you and the online questions afterwards. Thank you, great.
Thank you very much, Professor. You may have explained this, but just wanted to understand with the treatments, you know, well, depending on the progression, are they actually just stopping the progression because the cells that are dead, in fact, have already died, or is there any way to reverse that itself?
Sure, great question. So most of the trials are designed as their principal outcome to slow progression, but they do also look to see could they be improving function as well. But that tends to be a secondary ambition. I do think it is possible to improve function. So if you have a cell that is sick and you make it feel better, it should work better. And we certainly see that. So we see that in some of the drug studies, we see that in some of the gene therapy studies, that you can improve function. And, you know, of course, we want it all, we'd like both, but, you know, somewhere to start would be slowing or halting progression. But yes, improving function is possible. Clearly with stem cell therapy, you're looking to restore function because there is none. So you need to have improvement. So you're trying to restore. How much restoration is difficult to know. You know, it's not going to restore normal function. But again, I've learned from talking to patients for many, many years is that you don't need to restore normal function for it to have a really big impact on people's lives day to day. So I do think it's going to be possible to improve function that will have a meaningful impact on patients' lives. But the bar is ever increasing because people like Anna are providing us technology. So, you know, technology does provide significant improvements in function. So, you know, you've got to at least meet that bar with your therapy to be worthy. The only thing I'll mention about the genetics that I didn't mention is that there are genetic technologies also for the very advanced stages as well. So it's not actually just stem cell therapies. It's something called optogenetics, which is, again, you use viruses to deliver a light sensitive pigment to whatever remaining cells there are. So you try and make residual retinal cells light sensitive that wouldn't otherwise be light sensitive. And those light switches are becoming ever more sophisticated, and there are some companies that I've spoken with that are really very impressive how sensitive and rapid those switches are. So I think the possibility for improving vision at very advanced stages of many conditions is better than it was, you know, at least 5 years ago. And there is an optogenetics trial for Stargardt disease planned.
Thank you. Rhea, do you have a question for our online community?
Yes, I think there's quite a lot of informed people online at the moment. So one of the questions is about the metformin trial.
Yeah.
And where are we on that?
Yeah.
And related to that is a question about optogenetic monotherapy and how good that is, and the fact that the FDA have received fast track designation for that particular therapy.
Sure. So the optogenetic one is the one we just mentioned now. So there is a company that's looking to do that in a phase 1/2 trial. It all comes down to the light switch, and the more modern ones are better than the ones that are in clinic already. So I think the more modern ones are going to be faster, more sensitive, because you want it to be very sensitive. You don't want it to be so bright that, you know, and also you need it to switch on or not, you know, reset itself really quickly. Otherwise, it's not going to be useful vision. The other thing that would be optimal is if you don't need to wear, you know, gigantic goggles and carry a pack and all the rest of it. Some of the current ones, you do have to wear massive goggles and a pack, and a lot of people don't like wearing that kind of tech, not surprisingly. I guess you would if it provided you very profound improvements, but currently it's not. And the modern switches are not requiring those sorts of augmentations with goggles. So I see that as a win-win. So that is exciting. The fast track designation is, that's just a regulatory thing. It doesn't really mean anything. Everyone gets fast track designation. Don't get it overly, it's all good, but it's not sort of a, you know, it's part of the process you need to go through, right? The metformin study, it's unclear how metformin would work. It's a thought that it might have some role in stopping cells from dying or renewing. It's sort of, it's quite sexy in the aging world, isn't it, Franz? I think metformin. So, you know, but you know, I'm not entirely convinced about it. I've reached out to the NIH PI and he hasn't got back to me. I'll try and find out again where it's at. I think it's actively recruiting. I've not seen any results from the metformin study. I'll try again to reach out to the NIH PI.
Thank you. I think people are quite interested in that trial, and I know that some of our members did try to get on it. And just finally,
but sorry to interrupt, but I really would not. I would recommend people do not get hold of metformin and start taking metformin.
Thank you very much for that. And in line with that, just one final question about some people are quite anxious because this affects children. How safe are children going on any kind of trial? And I'm sure you want to tell people that they will get that information, but it would be helpful if you. Yeah,
it's a great question, and you'll be reassured to know actually to undertake trials in children or have children in any part of your trial is incredibly difficult to get through regulatory approval. So the bar is super high. Safety is absolutely paramount, and generally speaking, the FDA and the EMA will not allow you to include children until you've got safety in adults, and that's not even enough. You need to have shown that there's been some evidence of benefit in an adult before you include a child. And because of those high bars, it's actually put off a lot of companies from conducting pediatric studies, but I'm glad that some are now, because I do think childhood onset Stargardt disease is potentially a group that could help us get to an approval therapy quicker than any of the other groups, because as Franz has described, it's earlier onset and often it does progress faster than the other forms.
Thank you.
We'll take one more question from the room, and then I'm going to draw this session to a close.
Hello, I've got Stargardt, and what I see in front of the center of my vision is a lot of sort of scintillating spots, sort of flashing, and that's very tiring. And in some ways, I wouldn't mind not getting vision back, but if I could kind of get these spots to be less bright and kind of more subdued, that would be really helpful. So I don't know if the sort of research actually looks at what the patient actually sees.
Yeah, that's a great question. I'm glad you've asked that. There is some work to look at what might be the underlying cause of that. And in fact, I think one of the researchers is in the room actually, who's got some interest in these type of positive phenomena, the visual symptoms you're describing. We hear about them in lots of different conditions. It's not specific to Stargardt disease, and whether it is at the level of the retina that there's some it's gone a bit haywire, it's just shooting off all kind of randomly, or whether this really does represent the brain filling in the gaps, and so then referred to as a visual hallucination, or Charles Bonnet syndrome. Absolutely right. It could be both of those things. So a lot of people over time do tend to be able to ignore them. Clearly for you, they're very troublesome and you'd rather they weren't there.
Yeah, I mean,
It's still an issue, sure, absolutely. Some people find that if they are visual hallucinations, there may be certain behavioral techniques that can be tried out, or some people find there are certain things in their diet that, too much coffee or alcohol. There are specialists. I'm not suggesting you're drinking too much alcohol, or maybe you need to drink more alcohol. I don't know, but there are certain specialists in the country who have particular expertise in Charles Bonnet syndrome or visual hallucinations, and one of them is Professor Fitch at King's. So he would be someone worth seeing to see whether he feels your symptoms fall into that group of conditions, and there are things that can be done. But the number one is to reassure it's nothing terrible. It's easy for me to say that, but often people then worry that maybe they have a brain tumor, or maybe they're going mad, because sometimes they see things that are quite disconcerting as well. So thanks for bringing that up.
Thank you, Michelle. So I'm sure there are other questions, but both Franz and Michelle are going to be around during the day, so please do seek them out to ask your other questions. Fatima, can I just get you to come up? And we have a little gift for both Michelle and Franz, so thank you for your time today. I really, really appreciate it.
Thank you so much.
Very, very kind. Unnecessary. So you've been concentrating for a long time, and those are some big talks. So we are going to take a 20-minute comfort break, 25-minute comfort break. Tea and coffee is outside. For our people online, we will switch off the microphones and you can get a chance to just decompress a little bit and take some time. For those of you who are here, please don't forget we have a raffle going on. We can win some great prizes over by our reception desk. We have our flip charts where we are asking for your feedback on today and what's important to you, what you need from Stargardt's Connected. So please take some time to fill those out as well today. And also we're collecting people's stories. Ivan, our fantastic filmographer, and Rhea are collecting stories. So if you're approached, if you're interested as well, please do give your stories, because they really do help other people. And that's what we're really learning. This community is all about people sharing what they've been through, what works for them. And that means so much to those who don't have those kind of connections. That, I think, is everything. You are? Oh, yes, sorry. We do have, if you would like to tweet and share what we're doing today on social media, we are using the hashtag Stargardt2023. We'd be grateful for any promotion of what we're doing today. It really helps spread the word and particularly to help reach other people from our Stargardt community. And finally, if you do want to go outside at all, you are more than welcome to. It is quite warm, but please don't take any food outside with you. Please consume more food here, but drinks and taking a breath of fresh air outside are more than allowed. Thank you very much. We will reconvene about 12:15 in about 20 minutes or so. Thank you very much.